Hello, Innovation Stream friends. Wherever you are in the world, I hope you and your loved ones are healthy and safe. My name is Randy Bell, and I'm the director of the Global Energy Center at the Atlantic Council. Thank you all for joining us today for EnergySource Innovation Stream, where we highlight new energy technologies with the potential to reshape the global energy system. Today, we will be hearing from Amanda Simpson, the Vice President for Research and Technology at Airbus Americas, who will discuss how Airbus is exploring a hydrogen-powered, zero-emission concept aircraft called ZEROe. I have several reminders before we get started. First, you can follow us on Twitter at AC Global Energy and use the hashtag InnovationStream. Second, after Amanda's presentation, you can submit questions through the Q&A function on Zoom, and we'll get to as many of these as we can. If you're watching on another platform like YouTube, unfortunately, we cannot take your questions. So please let me welcome Amanda to the Atlantic Council. Amanda, thank you so much for joining us today.
Well, thank you, Randy, and thank you for inviting me to join in this conversation. I think it's not only important for the Atlantic Council, but for everyone to hear what's going on and what are the prospects for the future.
Yeah, I mean, the Atlantic Council has been doing a ton of work on hydrogen. Clearly, we're not going to be able to decarbonize the energy system without hydrogen. The question is what role it will play and what sectors of the economy it will be used to decarbonize. I'm really excited to hear about how Airbus is thinking about using hydrogen in air travel. So why don't we get started, and then we'll come to Q&A as soon as you're done.
All right, so let me go ahead and bring up some slides. All right, can everyone see that? All right, so let's move ahead. So I'm going to talk about clean aviation. Clean aviation, we believe, includes a variety of different sources of energy. And this is all to meet the goal of reducing our carbon emissions to half of what they were in 2005 by 2050. And as you can see on this graph, if we do nothing, it's after the recovery from the pandemic, we expect emissions would otherwise continue to rise at a 3.5–4% rate as they have historically as more people travel. Remember, we move billions of people around the globe every year. But there's going to take a variety of different efforts. And so on this chart, you can see, we're looking, airlines and our others are looking at using offsets today, but those are not long-term. So then we have a couple of things that we're already implementing. The use of sustainable aviation fuel, which is shown in this chart as green. We think that's going to be about half of the impact to get to that 2050 goal. We believe that operations, how we move aircraft through the sky and, quite frankly, on the ground, will have an impact. And that's that thin orange line. And then the blue line is new technologies that are going to be introduced. And we have to look at things today so that we can get them introduced to an aircraft that will come off the production line in the mid-30s. And once those aircraft start to get introduced, then you start opening up what you see as the blue wedge on this chart. And that will help us, all of these working together, to reach that half emissions by 2050. And there's a push to, instead of just going to half of 2005, to go to net zero. So all of these solutions, all of these need to be applied if we're going to make it. So I'm going to go through these a little quickly because we only got a few minutes. Certainly sustainable aviation fuel right now is available. We blend it into fuel systems. All of our aircraft are approved up to a 50% blend of sustainable aviation fuel. And by using sustainable aviation fuel, instead of using petroleum, we're pulling carbon out of the environment to create the fuel so that when it is burned at altitude, It's just replacing carbon that has otherwise been removed. So it becomes a closed system. And that's a big part of what we're going to do, particularly for the existing aircraft that are out in the fleet and for those that other solutions may not be able to apply quite for some time. The other is looking at operations. How we move aircraft. How do we make sure that, when an aircraft starts its engine at an airport, it's going to have a unrestricted taxi to the end of the runway, ready to take off, and can climb straight to altitude where it is most efficient, where it is the cleanest. Have a very straightforward route that takes into account weather and other geographic obstacles, and then have a very straightforward descent into the airport without holding, without intermediate level offs, to reduce the impact of the carbon being emitted into the atmosphere. And of course, you certainly then when you land, that you can actually taxi right to your gate instead of being put into a holding area or taxiing around the airport, waiting for your spot to open. We're looking at bringing automation into the cockpit so that the aircraft itself operates more efficiently, and using automation and artificial intelligence to make sure that even if systems on the ground aren't available to assist an aircraft, that the aircraft itself can find the runway, efficiently land on it, and regardless of the weather conditions. But what we're going to also talk about is hydrogen. Hydrogen is going to be that new fuel that's going to help us not just close the cycle on carbon, but actually stop emitting carbon to begin with. And there's three things that is about hydrogen. Not only does it not emit carbon, it's also going to reduce those other greenhouse gases, such as nitric oxide and even cloud formations and contrails. Because when you burn hydrogen, all you get is water. So what we're looking at is hydrogen can be used three ways within aviation. You can burn it in a turbine, just like we burn jet fuel today. The aircraft have demonstrated the use of hydrogen in turbine engines all the way back to the mid-50s. So this isn't new technology, it's just optimizing it for long range use. Another is for hydrogen fuel cells, where you take hydrogen, combine it with oxygen, create electricity, and use that electricity to then drive electric motors, which are either connected to a fan or a propeller for propulsion. And of course, the third is to use hydrogen to actually create synthetic aviation fuel that is no longer requiring the products for closing the loop of carbon, but actually just pulling carbon out of the air, combining it with hydrogen, and creating synthetic aviation fuels. So what are the challenges? Hydrogen is great because it has 3 times the energy density by weight as compared to jet fuel. The downside is that it takes up 4 times the volume. So you have to look at how do you maximize the amount of energy you get per unit volume so that we can carry that into the sky, because volume is weight when you build a tank and have to put an airplane around it. So those are the main challenges, as well as the ecosystem that exists today. In the United States, we produce and consume about 10 million metric tons of hydrogen, but that's mainly going into agricultural and industrial uses. Supplying the transportation industry, and aviation is not alone on this, is going to be a new challenge for the hydrogen ecosystem. So what we have done is put out 3 concept aircraft that we believe could be put into service in the mid-2030s. You see the top one looks like a traditional turboprop, but if you look at the fuselage, there's no windows on the back third, because that's where the cryogenic liquid hydrogen tanks would be. Also, when you take the fuel out of the wings, you can optimize the wings to be more aerodynamically efficient, have a higher aspect ratio, meaning that they're longer and thinner so that they are more efficient. On the bottom, you see a traditional turbofan aircraft. Again, standard tube and wing. We believe that we can build a aircraft that looks very similar to what you have today. Fuel in the back third of the fuselage, carry about 200 passengers, go about 1,000 nautical miles. In the middle is a more revolutionary concept. We call it our blended wing body. Again, 200 people, 2,000 nautical mile range, but the aerodynamic shape is optimized for efficiency and for handling the liquid hydrogen tanks. Now, all of these have what we call a hybrid hydrogen turbo engine, which means that we're burning liquid hydrogen in a turbine, just like we burn liquid fuel today, but that turbine is optimized for cruise at altitude. The energy you need to climb to altitude would come from an electric motor on that fan. And the power from that electric motor would come from a fuel cell, which would use gaseous hydrogen that is boiled off from the liquid hydrogen tank. So you have a combination of different propulsion sources all on a single engine to give you the most efficiency and reduce emissions. Another concept that we announced earlier this year, and we call it our pod concept. And as seen here, this aircraft has 6 pods, all of them identical, and every pod is a completely self-contained energy system. A liquid hydrogen fuel tank, an exchanger that would allow that liquid to become a gaseous hydrogen, go into a fuel cell, create electricity to drive an electric motor to drive a propeller. So this is a completely electric system, no turbine, but you could adjust the number of pods based upon the size of the aircraft that is being designed. The nice thing here is these pods are completely interchangeable. The pods can be quickly downloaded for maintenance. It's an innovative concept that we're looking at. Now, when we look at all of these are trades that we're evaluating over the next few years. I'll get to the timeline here in a moment. But I want to tell you about a project we just kicked off a few weeks ago. The Ascend project looks at the downside of using an all-electric system, because we're talking about megawatt-powered electric motors. And anyone who's worked with those types of electricity in the megawatt range, running at thousands of volts, know that there's all sorts of problems. So what we're looking at is how do you cool this using the cryogenic liquid you have on board, i.e. the liquid hydrogen fuel. And by using that, we can get to the point where the wires and the motors can all be now superconductors that are cooled by the cryogenic liquids. We believe that we can get efficiencies twice of what they would be today and reduce those high voltages from, say, 3,000 volts down to something reasonable like 500 volts. And that makes a big, big difference when you're designing something to operate at altitude where the air is thinner. So this project is currently kicking off. We're very excited about this concept and how it could be applied to any of our concept aircraft. So we're looking at a lot of different venues, lots of issues. We want to make sure that when we are ready to move forward on this project, not only we're taking into account the environmental impact, right? But we want to look at the entire ecosystem to support this and other aerospace projects. We want to ensure that it is not only economical, but absolutely safe to the traveling public and to the people on the ground. There's the whole ecosystem that has to be evaluated before we present this to our customers. And we're certainly not doing this alone. This is a very cooperative project. We're working with different engine manufacturers. We're working with technologists who have experience with cryogenics. We're working with research institutes on aerodynamics, on new materials. The list goes on and on and on. This is a big project that is moving technology forward, not just for the aerospace industry, but for all uses of hydrogen. We're going to leverage what we've experienced in the past and then give back and move all of that forward for the future. So here's our timeline. We kicked off the ZEROe program about 3 years ago. We went public with it last summer, and we're keying on a mid-20s decision date on what we are going to do, right? Gathering all our stakeholders and deciding this is what we're going to do. We're going to now launch a program, start into the detailed design, develop the manufacturing and industrial system around that, and build prototypes, go for certification, and have an entry into service by 2035. It's an ambitious project, but we believe it is absolutely possible because we are committed to having sustainable aviation available for the traveling public. So with that, I think I've done that about amazingly quick, and I'm going to turn it back to Randy.
Amanda, thank you. That was fascinating. I mean, just so forward thinking, really looking at how to solve this challenge of aviation emissions in a way that is comprehensive, but also like looks to the future and what we might be able to do in the future. I have a bunch of questions. Of course, in the audience, if you have questions, feel free to put them in. So I want to first talk about, you mentioned near the beginning of your presentation that hydrogen is not a new technology in aircraft. So there's a whole bunch of other things that you need to innovate on to really get the plane there. The hydrogen piece isn't actually the biggest challenge. What would you say are the other parts of the aircraft that need to be solved in order to achieve this vision?
So, hydrogen propulsion, like you said, has been around for a while. And the Air Force flew a demonstrator in the mid 50s, and the Soviets actually built an airliner completely powered by liquid hydrogen in the 80s. But those were demonstrations, and they were of limited duration. What we're talking about here is designing an entire system that is reliable and sustainable, and looking at how to bring this into the airport environment. Certainly, hydrogen is a different type of fuel than kerosene. It has absolutely some fantastic advantages in handling, but it also has some negatives in handling. We spent decades learning how to handle kerosene safely. But, I've shown up to an airport once or twice and had my aircraft surrounded by fire trucks because someone spilled a little bit of fuel, right? With hydrogen, it's going to be different. Spilling fuel is not an issue, but you have to deal with the cryogenic temperatures. Cryogenic temperatures, once in the aircraft, apply not just to the fuel tank, which is going to be ultra lightweight and dually insulated to make sure that it doesn't boil off, but it applies to all the pipes, the valves, the pumps, all measurement instruments, all the things that we have spent decades developing for kerosene now have to be either adapted or reinvented to ensure that they can last years and years and years in a hydrogen environment.
Got it. Thank you. We're starting to get a ton of questions in the Q&A, which is great. I want to ask one more of my own questions before we go to them. So do you imagine, when you're thinking about this as a system, do you imagine that the hydrogen planes would be used on certain routes where you use SAF planes on other routes? Do you see that as a transition from one to the other, or how do you think about this if this becomes commercial in 2035? What does 2035 look like versus 2050 versus 2075?
I think we all wish that we could snap our fingers and that all aircraft in the mid-30s would be converted to run to hydrogen. But there are, 15,000 airliners out there, and they're not going to go away. So they're always, as long as they survive, going to have to run on some sort of clean aviation fuel. And SAF, sustainable aviation fuel, is going to be their solution. Also, what we're looking at today, and as you saw on the chart that I showed, there's a limitation, we think, today with today's technology on how many passengers you can carry and how far you can fly. So the initial aircraft that will start coming off the line in the 2030s are going to be probably the shorter range regional type hops. We're not talking about, transoceanic flights. As we know more about how to operate and the technology advances, future generations and iterations of aircraft will start to go farther and carry higher payloads and start to replace some of those bigger aircraft that we have today. It's going to be a transition period. This is not you stop using kerosene and you start using hydrogen. There's going to be an intermediate period that will probably last decades.
Thank you. Okay. I want to go to the audience because they just keep coming in. You mentioned safety a couple of times, and John Mara has a question. It's an interesting one, and I'm not an aviation expert, so I don't even know if I think it's a really good question. But if it's not, sorry, John. But so, what do you do in the event of an in-flight emergency that forces a fuel dump to avoid an overweight landing? How do you think through that with hydrogen as the fuel?
Well, hydrogen is so much lighter that when you remove the weight of the fuel, it's not going to adjust the center of gravity as much as it would with kerosene. That's why it's very important with kerosene or jet fuel to have it right in the middle of the airplane in the wing, so that as you burn it off on a flight, you don't change the balance of the plane. Hydrogen, quite frankly, most of the weight's going to be in the tank itself. So if you were to dump it, for instance, which would be highly unusual because it isn't going to contribute much to the total weight of the aircraft, it's not going to adjust the center of gravity or the weight very much.
Got it. That's really interesting, and just a different way of thinking about this. Okay, Barbara.
Let me add, Randy, because this is the other nice thing about hydrogen. If you were to vent it, if you were to dump it, hydrogen is lighter than air.
Yeah.
It goes up.
Yeah.
It doesn't fall to the ground. It doesn't contaminate the sky. It just evaporates and enters the atmosphere, which already has a lot of hydrogen in
it. Right. Okay, Barbara Berger asks if Airbus has started to think about manufacturing, and will these new models use existing facilities, and will at some point Airbus start winding down existing production to replace with these new planes? And I think this actually touches a little bit on the last question I had, more from the sort of the production side. How do you see that?
Yeah, well, certainly a production decision is going to be years away. And where the aircraft is going to get manufactured, will it replace existing models or production lines? Those are decisions that will be made over time as the aircraft enters the system. Right? We're building hundreds of aircraft a year right now. In 2035, ZEROes will probably be coming off in a much smaller number than that. So whether you are building new facilities or whether you're repurposing existing facilities, those are decisions that are still years away.
Got it. Okay, I want to combine two questions that are related from Richard Morningstar and Heinrich Kreft. So Heinrich asks if Airbus competitors are working on hydrogen planes, and Richard Morningstar asks, if you work cooperatively with other manufacturers, could you actually speed up this technological development?
I think everyone in the aerospace industry understands that there needs to be a replacement for kerosene and, Jet A. And we're looking at a variety of different options. We think at the low end for smaller vehicles, that advanced air mobility concept, batteries, which are very, very heavy and have limited power and take forever to recharge, will have a niche, right? And until we figure out how to replace those long-range, large transport aircraft, SAF is going to have a niche. Mm-hmm. But in the middle, hydrogen apparently seems to be the solution. And we are not the only ones working on it. There are a lot of small companies that are developing concepts or even flying demonstrators already. So yeah, I think there's a concerted effort. We're working across various other industries. A lot is going into the automotive and truck industry, and we're pulling technology from them as also contributing back to them as we are advancing as well. This is not a one company or even one industry solution. This is something that is going to be much, much bigger than that.
Fascinating. Okay, I know that these are still concepts, but there's a performance question coming from Pierre LeBlanc, which is would there be a negative impact on speed? So how do they imagine the planes will perform?
So the concepts that we showed, the turboprop or propeller aircraft would operate at around the same speed. I think it's like just under 0.5 Mach that the planes do today, and the turbofan aircraft, whether it's the standard tube and wing or the blended wing body, would operate again at the approximately 0.8 speeds that we see today. So no, it would not impact the speed of the aircraft.
Got it. Looking at those designs, you see the big hydrogen tank in the back or in those pods. So you have, for the same size plane, fewer passengers. Does that impact do you think that will impact the economics of air travel in any way?
Well, certainly, we try to optimize the amount of payload that an aircraft can carry. So by reducing the payload, i.e. the number of passengers or the amount of cargo that you carry, will indeed impact the economics. But we believe that operating hydrogen will become more economical, and most of the cost of operating an aircraft over its entire life cycle is not the acquisition cost of the aircraft, it's fuel and maintenance and all the other things that go along. So sustainability is not just clean environment, but it's also how do you sustain and maintain that aircraft over time. And that's what we're designing for.
Got it. Okay. Two more questions. One from John Sewin, who works with us at the Global Energy Center. I think this is a great question. What are the challenges to promoting hydrogen use in the air freight sector? So where the aircraft are used for well beyond 30 years and cargo volume is a concern. Are we going to see any of that, or is that SAF in the short?
I think the larger aircraft that we have today will continue to use SAF as technology with regards to hydrogen or other fuels. As we learn more, we start using it, we will find that approaches that can be applied to larger aircraft, whether it's hydrogen, I think it will be, is yet to be seen. But that's probably a couple more decades away.
Got it. Okay, final question, since the Atlantic Council is a policy shop. What do governments need to do to help facilitate the adoption of a range of clean aviation technologies? I don't want to just pick one winner, but what do you do to set off a range of innovation, including hydrogen, but also SAF, also on efficiency, all the things that you talked about?
Well, I think we hit on it with an earlier question. The big barrier moving forward is economic. Certainly today, hydrogen is more expensive. Batteries are more expensive. All the alternative fuels either are more expensive or the infrastructure to support them doesn't exist. So where the role governments can play is to help motivate, help alleviate some of those barriers so that early adoption can be put in place as the cost gets driven down, as the infrastructure gets built out. That's where public policy can make a big, big difference.
Amanda, thank you so much. Unfortunately, we are out of time. Thank you all for tuning in today. And really, thanks, Amanda and Airbus, for this really interesting technology. Really want to see how this develops over the next 10 years. You can follow Amanda and Airbus on LinkedIn and Twitter to learn more. I'll let you all know about a couple of other events happening this week at the Global Energy Center. So tomorrow morning at 9 a.m. Eastern, we're hosting the final event in our Raising Ambitions series, which is on African and South Asian perspectives on the Leaders Summit on Climate that happened last week. So African and South Asian perspectives on the announcements we saw last Friday, I mean. And then on tomorrow as well, we're hosting an event with Senator Joe Manchin to discuss prospects for the energy transition in the Appalachian region, and that's tomorrow at 10 a.m. Eastern. Thank you for everyone who helped put this event together, including Candace Johnson, Roger Morales, Mary Castillo, and Olga Kova. The presentation will be available on the Atlanta Council website, YouTube, Facebook, and Twitter pages. So please share it with your colleagues. And we will have another innovation stream in a couple of weeks. So tune in and we will see you then. Thanks so much.